Okay.
Okay. Well, the first thing I would want to do is I'd like to pass around a booklet I wrote, which newer attendees may not already have. And even if it is it is only somewhat related and optional to this talk, but it still may be interesting, and I'll be back in a moment. Here.
Go ahead and make some comments. There's not that many
You can share.
here. Yeah, in fact,
Again,
Keep your microphone higher.
Quite a few of you already
if you want
have,
more, but he doesn't have that many. I gave 3 to the first table. Now I don't.
New people may find it a little interesting.
Anybody else?
You got another?
Okay. Well, start. This talk is motivated by the question, why does the simple hydrogen atom, that is one proton orbited by one speedy electron, have less mass than the previously greatly separated electron plus proton when they were free, unbounded particles? So those parts previously were at rest, were drifting slowly with respect to one another or close to rest. I used to believe, and even wrote, that the opposite of what is shown was true, that rather the free unbounded particles were lighter than the orbiting system, because I thought that the fast, speedy orbiting electron would incur a relativistic mass increase. Therefore the hydrogen atom should be more massive, somewhat like the protons accelerated to a high speed by the European Super Collider. But empirical data from the National Institute of Standards and Technologies, NIST, indicates that for the hydrogen atom, it has less mass after it forms, and less by an amount of mass that seems approximately equal to the proton's equivalent mass that was emitted by the hydrogen atom when it was formed. I'll just say photon's mass from now on instead of a photon's equivalent mass. If NIST is right and the hydrogen loses mass when emitting the photon, that locks us into accepting that the photon has, at least momentarily, a particle-like characteristic, and likely similarly when the photon reaches its target and is absorbed, and thus the target's mass increases. Now, this talk tries to explain why NIST is likely right about the simple hydrogen atom's mass, and I'll outline a few more of the many interesting inferences that should be likely drawn from that. But some of my inferences may go too far, and you, with your own reasoning and knowledge, might rightly take some exceptions to what I say. I will often be talking about very small variations away from the simpler value, the latter usually sufficient for most purposes, but historically noting slight exceptions, even though hard to measure, have often made a big difference. For example, take the ultimately no longer needed theory of phlogiston and its supposed loss or release during burning. But it took very accurate scales and care to show that the burnt residue gained weight, not lost weight after burning. Yet that small difference greatly advanced chemistry. And another example is the ultimately no longer needed they were small little epicycles in Ptolemaic theory, when Kepler and Newton abolished that little need, the advancement of astronomy was greatly enhanced. Now, it seems very likely that hydrogen atom lost a little bit of mass when formed, and thus its electron, proton are both also lost mass. And so it seems likely that the helium atom, when formed by its two orbiting electrons, should also lose mass. And similarly, for all other atoms, or most others, when they are so formed by their electrons, and likely similarly for molecules with their, when formed by atoms with their electrons coming closer together, all of those are exothermic reactions also. And similarly, in the case of nuclear fusion, with its many magnitudes more energy emitted and much greater mass lost, all of which are well known. That is much greater mass lost and stronger bonding than in the chemical bonding previously described. So the chemicals case, with its somewhat close orbiting electrons, but still not nearly touching, may be merely a microcosmic forecast of the nuclear actions with their nucleons touching or nearly touching. Thus, the long-known chemical case, a precursor to the nuclear case studied later historically. Thus, despite the likely fast-traveling or vibrating parts arising in both cases, mass was lost and no relativistic mass was gained inside those chemical and nuclear systems. And lastly, consider gravity, and thus particles are bodies in the universe that orbit very massive bodies at high speeds. Maybe they have lost a little mass too compared to their masses when they were previously much further apart and just drifting. However, I'm somewhat doubtful of that because each particle of, say, our moon orbits the Earth with drastically greater angular momentum than a Planck's constant worth, and thus the whole Bohr atom mass loss paradigm and its quantum world may not apply to gravitational orbiting of a massive body and far away from it. Yet, if charged particles in a gravitational orbit do give off radiation and incur a relativistic mass increase, that would violate Einstein's second 1905 paper on special relativity. It seems to me likely that only atoms and their small parts and molecules can closely engage small ether cells or grains in the small quantum world and nearby atoms. That is the countless many little nano worlds that make up our big world. That is, in these small realms, the small Planck's constant worth of angular momentum that those small particles have correspond with simple numerical multiples of the angular momentum of the average ether grain. And that makes possible a long list of exceptional behaviors quite opposite of what we are used to in our large mega world. Such exceptions are likely frictionless orbiting, no electromagnetic radiation emitted every completed orbit, success regarding superconductivity and superfluidity. I'd say even immunity from the second law of thermodynamics, and even the continual restoration of the world from the otherwise negative consequences of that downhill second law. And that sheltered small world also supports the phenomenon of mass loss with high velocities instead of mass gained with high velocities. All that due to the special supportive ethereal pressure gradients there, I believe. Now consider the large number of particles in this universe that have lost mass by coming closer together due to electrostatic attraction. That forms fast orbits, and the fast orbits of nucleons within a nucleus, consider them due to and the strong nuclear forces. Those total mass losses may be very roughly equal to the total mass gains by other particles in the universe. That is, many particles also gain mass using high energy accelerators, violent expulsions, or the like. The latter powerful expulsions have sent particles traveling in rather straight lines and too speedily to be held in close, tight orbits. That dichotomy, the total mass gained, that dichotomy, the total mass gained by some fast-moving particles versus the total mass lost by others, may constitute a balance fundamental to our universe. Now we'll go on with slide 2. Okay,
I'll get it small.
it may have to get quite small. Okay, so we'll try to return to the question: why does a particle gain mass and increase velocity under some circumstances, but lose mass with increased velocity in other circumstances? Ultimately, I think it is due to our living in a universe consisting of very low density pressurized ether occupying over 99% of the universe's volume versus very high density particles occupying less than 1% of the remaining space. This leads to a relatively low speed and energy that a particle can develop when sucked into a near empty volume, say adjacent it, that is equal to the volume of that particle that particle occupies. A pressure times a relatively low volume roughly equals a low energy, and the amount of angular momentum is very limited for a compact small volume particle, even when it spins at roughly the speed of light. But contrast that to a particle that is powerfully accelerated to a very high velocity in a rather straight line through the ether in vast space. Then there is almost no limit to the vastness of the volume of space and the ether in it, nor a limit to the product of pressure times volume equals energy, and all that inferred from the small percent of the vast universe occupied by conventional particles, a subtle asymmetry built into our universe, almost too subtle to take notice of. So in those circumstances where a particle gains mass with acceleration, I think that's like a billion photons hitting a proton on its back face almost all at once. And forcing it forward against an ether with a standard ethereal density and pressure at its particle's front face. It is like an aircraft carrier's quick catapulting of an airplane from momentary stationary state to a high takeoff speed, as I try to show below it in the sketch, and the pilot can feel the great discomfort, including the pressure on his back and great squeezing. That contrasts with another particle that loses mass when accelerated, that I try to show up there. likely that I think that is like being sucked into a lower pressure and density gradient or ethereal region from a region not quite as low on its back face, likely a uniform pressure gradient permeating the particle. That is more like an astronaut near Jupiter and experiencing an accelerating natural free fall toward Jupiter, but the astronaut just feels comfortable, like he is comfortably drifting, and with no pressure or squeeze on him. And similarly for an electron orbiting a proton, as long as it remains in that special pressure gradient, then its spin or vibration may perhaps even exceed the speed of light or its dimensions stretch. Incidentally, when two particles orbit each other, we're talking about an average absolute velocity, not just a matter of opinion depending upon one's relative viewpoint. Often simplified views of or examples of general relativity will picture a web-like pattern of space-time that is distorted or curved, more curved toward bodies. But I prefer instead to picture a real flow of ether that is curving near bodies, a Venturi-like flow constriction, and a related suction or attraction developing there. Now, all the above rough discussion may not be ideal or perfect, but hopefully it is somewhat helpful. So now we will turn to a brief discussion of the photon and go on to the next slide with regard to the photon. Okay, that may have to be made if possible. Well, that's plenty small enough. Thank you. Okay. I think the photon is a pseudo-particle for various reasons. It is basically not like a more sturdy conventional elementary particle such as an electron or proton. And I think likely that thus photons behave differently under gravity compared to an electron or proton or a group of atoms, of hydrogen atoms or whatever. We'll assume here the view, say, still held by most scientists, that the speed of light is constant in space, and that a light pulse or photon decreases in energy and mass when moving away from a gravitational body, and increases in energy and mass as it approaches a large gravitational body which tries to pull it forward. And here we try to show a big photon or a high mass photon that is decreasing in mass and energy as it leaves one body and increases in energy and mass as it gets closer to another high mass body. My first conclusion is that the photon first lost some mass, some of its mass, to a real ether in space, and thus further increased the already considerable amount of real mass contained by a real ether already in space. And then approaching a big, distant, gravitational body gains back a comparable amount of substitute mass from a real ether in space. But naturally, it does not grab back the same ether grains that it lost to the ether, say, a light year earlier. So that long time traveling photon mass is no longer made up entirely of the same ether grains that constituted its original mass. And that is because it acquired, as implied, some substitute mass from the ether near the photon's final target. And that automatically is a major wave-like characteristic, but not one often mentioned, unfortunately. Again, a major wave-like characteristic. The particles bundle that leaves, if one compares it to the final destination, is no longer may no longer be made of largely the same grains that it, or whatever that it had when it first departed at its origin. My first conclusion is that the photon, and let me see exactly where I am. Okay. And note the following Compton studied aspects of X-rays or a photon, and my references, inferences, and here we show it below. So we'll concentrate on this as this high energy photon bounces back and forth, as it goes along. Imagine that photon travels in an overall pretty straight line, except for being deflected first somewhat to the left and then an equal amount to the right, say 100 times, and that those deflections were caused by encountering electrons at rest or moving slowly close to its path. After that, the photon could likely have almost no mass and no energy remaining. But that outcome cannot happen with the sturdy proton or electron traveling that path, regardless of the deflections along the way, and regardless after that of whether it is traveling at its original speed or zero speed. The outcome is very different from the photons. The final true elementary particle will still have, roughly speaking, its standard rest mass, or perhaps an even greater so-called relativistic mass, and that sturdiness differentiates a conventional real particle from the photon pseudoparticle. And the pamphlet and some of my previous work that I passed around tries to indicate why real conventional particles tend to be sturdy, especially compared to the photon. Now before closing, I want to say some more words, and may involve a page or so, to add my opinions about Einstein's first and second 1905 special relativity papers. His first treated internal mass gain versus internal velocity gain in a way that was either wrong or unclear, and he later told a colleague that he regretted that. But in his second paper, he just said in effect this: if a body emits radiation or a photon with energy E, the emitting body loses a mass given by it loses mass given by the emitted energy E divided by the speed of light squared. That was likely right and constructive, or at least very close to perfect, because he did not confuse things by speculating about the relative motions and velocities of internal parts and whether or not that caused mass changes. And about 8 years later, Bohr made some progress, some good progress, by helpfully theorizing about motions of individual parts and how that caused the resulting events. However, for an electron orbiting the proton, elementary textbooks generally still use the electron's rust mass instead of subtracting from that the very minute photon's mass. That is a very small discrepancy, but we'll leave that to some very able specialist to address. It is possible that internally E may be a pinch greater than MC squared. It seems to me interesting to note that sometimes, not always, a free neutron decays into a low kinetic energy electron and a proton and a hard to find, very evasive, even controversial antineutrino. That antineutrino seems to go through hundreds of feet of barriers, and although I think its angular momentum is sometimes detected by very expensive sensors and setup, I doubt if its mass and energy are accurately located or measured. Somewhat similarly, if an atom or particle decays and the resulting electron tries to escape from a body with a very high gravitational field, that electron's initial high velocity and large relativistic mass may be greatly reduced before it finally is rather free from gravity and can manifest itself generally. I think the electron then has lost a lot of its initial mass and energy to that ether, an entity that Einstein often thought did not exist and the mainstream still denies existing. That leaves the paradigm of a high-speed emitted electron from near a massive body, and that electron's MC squared not ultimately able to manifest as much MC squared energy when it gets deep into outer space. That is compared to a similarly emitted electron, but emitted far away from the high gravitational body. I don't think one can then properly say that the manifestable MC squared of one is equal to the manifestable MC squared of the other. Einstein, in effect, admitted that dilemma when he said in a speech in 1930 that so-called empty space seems to eat matter and energy up and still remain empty, a seemingly observable fact and problem, except that he thought and hoped that his theories could somehow evade that problem. But I think, as has been said better by others, that there are some self-contradicting things, partly self-destroying and inconsistent things in Einstein's relativity theories. I think that some important parts, like E equals MC squared, have considerable merit, but even that has limits, and I think Einstein's interpretation and clarity, and that of mainstreams, needs to be at least modified and greatly improved if its usually good accuracy is to be extended and be more encompassing and clearer. Thank you, and now for any questions and discussion, if time allows.
I've looked at the mass of all the nuclear isotopes that NIST lists, and at each end of the spectrum, among the low, like helium and some of the others, the mass is greater than the sum, but in the middle, it's less, and hydrogen is one. It's less. But for instance, uranium, the mass of uranium is more than the sum of all the parts.
Well, yeah, whether there's something that I may have been very unclear about. I'm not trying to clarify. I'm not trying to discuss how much mass is lost, say when when helium is formed, and later when atoms are squeezed together, mass can even be gained. That is, with regard to the nucleus, all I'm talking about is the mass of well, going back to the first slide, if possible, the mass of a nucleus sitting there without electrons, plus the mass of the electrons at quite a distance that haven't joined it, that mass compared to the mass of the joined parts when the electrons finally come real close to the nucleus and begin orbiting it. So, in other words, I would be comparing here. Pardon me if I could just. I'd be here. I would be comparing the mass of the nucleus of 2 protons and 2 neutrons orbited by 2 electrons with regard to helium, 4 nucleons seated over here, 2 protons and 2 nucleons, and 2 electrons sitting here. Sorry if I said 4. And I would say, although I don't, NIST does not have this data estimated, at least not with super accuracy, the mass of the free parts compared to the orbital system. Okay, go ahead.
Maybe allowed to comment something here. Even in regard to the questions that just was
Pardon?
asked. So, I mean, in my view, it would be very important.
Yeah, it's hopefully, I think it's right.
So, if it would be okay, it's for me to comment.
Put your mouth right against it.
Yes. To comment in general on this presentation and related to the question that just was asked, I believe that it will be very important to consider this very elemental problem and anomaly that has been detected. And I think that this approach with involvement of the ether as a, in my view, as a substrate of all the phenomena will be very important. In that way, I kind of support and think that at least involving the ether and the pressures and the gradients and so on would be the right way to explain this very elemental and very basic problem. And just would recall or remind audience to the movie that was shown yesterday with the lightweight and the gyroscope that he was like turning around after being again turned around itself, and we saw actually that was very drastic change in the weight. So now this looks like formally comes something like as a model of what Professor Lightweight was showing in that video. So really, they should be looked at and considered and explained at this very elemental level. And then other issues like, you know, increase of mass and so on could be then try to be explained along the similar lines and same lines. Thank you.
It's important. I would say that this talk, anytime anybody says even that it's stimulating with regard to questions and thinking that arise. I think that is my main purpose. I just want to relate maybe a funny story. It sure wasn't funny to me. There was a blog or whatever online, an online discussion, and this question arose. Which is heavier and why? And some people said, well, we don't care too much about the data because we don't think it's accurate enough, although I reviewed the data, and the claims of the accuracy of the data are, they take things out enough to so many decimal places that the impression is that it's plenty accurate, but probably the least educated people in this discussion group said, why, of course the hydrogen atom is lighter after it forms, because there's such a thing as ionization energy, and it takes energy that you have to put in the atom in order to ionize it into a proton and electron. And I guess the implication is that since it takes energy to do that, it takes added mass as well as added energy that goes along with it. But I, almost like a somewhat overeducated person, said, oh no, I've studied physics. There's a relativistic mass gain. You can't say that is that speedy electron, that this thing has not gained weight, or at least it has maintained its mass and not lost mass. So that shook me up a little bit and made me re-examine a little more vigorously I'd seen a movie in which Stanford, very knowledgeable linear accelerator person said, the first thing we want to do when we get rather new people to this is to explain that velocity does not always lead to mass increase. And so I kind of learned that, or double hard.
Okay, any other questions? Go ahead.
I have a question that anybody can answer the end, right? It is a simple question. In measuring mass of a particle of nuclei or smaller, is the dependence on velocity the only way to make the measurement?
Well, I'm not an expert on this, but my guess is that
Microphone?
you put these things in you can put things into magnetic fields like Warner and others did.
My guess is that among the things you can do is you can put atoms into magnetic fields and find out whether that causes an energy increase or an energy decrease, especially if you can align those atoms one way and then put the magnetic field on them. Maybe this is a way to study, so to speak, in this primitive model, whether your orbiting is speeded up or your pull between, so to speak, your proton and electron is increased in the magnetic field or whatever. I mean, perhaps these are some of the tricks. that they use it. I wish I were an expert in the NIST details of how they came up with their figures. Most of the time this stuff is very indirect, and it is by no means putting them on a simple scale.